Okay, so from today, we will start the detailed content of this particular course, that is flexible AC transmission system. As I was told you in the last lecture that flexible AC transmission system is nothing but the AC transmission system, that is conventional AC transmission system, along with some power electronics based controller added with it in order to modify its electrical parameter so that we can control the performance of it. Means as the performance of a transmission line is determined by or governed by the electrical parameter of it, that is resistance, inductance, capacitance and conductance. So by regulating that parameters by means of some static or power electronic based track devices, then automatically it will regulate its operating performance, that is under steady state condition or transient condition. As a course, it has objectives like the student should be able to understand the fundamental concepts of this flexible AC transmission system, and whatever flexible AC transmission system controllers are there, that is static or alternate based. So the operation of them along with their effects on improvement in the performance, operating performance of a transmission line, that we have to learn. At the end, obviously, the outcomes are students means you will be able to illustrate the different aspects of flexible AC transmission system or the conventional AC transmission system. Means what are the limitations of conventional AC transmission system and how that limitations can be overcome, or maybe we can say extended to overcome by means of an tax controller, that you will understand. Similarly, second module, that is basically on load compensation. So like transmission line compensation, in which we modify the transmission line parameter. Similar to that, in load compensation, we modify the parameters of the load, and by means of that, we modify the reactive power absorbed by it, and that ultimately affects on the performance of the transmission line, because that load is connected to the transmission line itself. Obviously, whatever it will draw, that is going to decide the operating efficiency or all other we can say characteristics of the transmission lines. So that is improved. Then in third and fourth module, we are going to see the specific static series and shunt compensators. So how we categorize them, what are the different types of them, then what are the benefits we got out of them. So that all details we will see in module 3 and 4. Module 5 is going to describe the fundamental concepts of voltage and their angle, that is called as phase angle. So how voltage and phase angle can be regulated by means of some tap changing transformers, or maybe some alternate based phase controllers. So that is described there. And in last module, specifically the unified power flow controller, that is explained in detail along with its circuit diagram, and its operation can be understood by means of an graphical approach, that is phasor diagram. So let's start with the module 1, having titled facts concepts along with general system considerations. So first point in that is transmission interconnection. So as we all know, the transmission lines are interconnected to each other at different buses. Means if we took the example that practically there are many more buses in the power system, and that all buses having some sort of interconnections with where these buses are either having generators along with local area load. Some buses are only the load buses we can call there according to development of the infrastructure or the requirement of that geographical area, we can say. So here if you see our simple power system I has been drawn. It is having an two generating stations. Total it is having an five bus bars. So out of that five bus bar, only two locations there is a generating stations, and obviously at all five locations there are load. So why we need to transmission lines interconnection? That is first of all we need to understand. Rather than this, rather than this, suppose we have an isolated power system. That is one generator is connected to the load, or maybe this generator is connected to the load to a transmission line. Let's say one generator is connected to a load to a transmission line. That is, we call it as a single machine system or isolated power system. What is the drawback of this isolated power system? Can anybody answer it? What are the limitations of such an isolated power system? It is like that one residential building is not connected to the utility grid. It is simply fed through a sorry. It is simply fed through a one diesel generator set up in that building. It is like that one generator, that is diesel generator we can call, is connected to the one residential building. Rather than that, there is no any other source connected to that building. So what will be the limitation of it? Can anybody judge it? Hirayu, are you there?
Yes, sir.
Yeah. Can you tell me if suppose there is a one residential building which is not connected to any other utility, it is simply fed by one DG generator which is owned by that society itself, and through that it is supplied. What will be the limitation of that?
So the DG set cannot totally supply the building.
We will have that DG set of that much power rating, no, of what breathing load is there.
In case of failure of the DG set, there is
Then
nothing for backup.
yeah. So that is the main limitation we can call. Don't think about the rating and that all. Here, it is an isolated power system. So to understand it clearly, I just give you the example of a residential building. That's all. So here, in this isolated power system, if this generator fails, what about the continuity of supply? It is not yet maintained, no? Are you understanding what I am saying here?
Yes, sir.
Yeah. So if the generator fails, the continuity of supply will not be get maintained. That is the one we can say contingency to which we can not write. Similarly, okay, this generator is okay, but if the transmission line fails, means some sort of fault happens on that transmission line, so because of that, the circuit breakers which are there at the end of this line, suppose for an example, will get obviously disconnect this transmission line. So under this circumstances also, under this contingency also, whether the load will get supplied through the source. Please tell me, if the transmission line fail in this isolated power system, will the continuity of supply will be maintained to the load by the source? Yes or no?
No.
No. So here what happens? In an isolated power system, in an isolated power system, if generator outage happens, the supply will be get discontinued. If the transmission line outage happens, supply will be get discontinued. So in other word, in technical word, we call it as a reliability. Means whatever this isolated power system is there, it is very less reliable actually. It is very less reliable. So if I want to improve its reliability, what should I do? What I have to do actually for that? I have to add up one additional generator along with this generator. Other will maintain the continuity of supply. Got it? Are you understanding what I am saying here?
Yes, sir.
Yeah. So in order to improve the reliability, I need to keep the reserve. Earlier, whatever was the load, suppose the load was of 100 megawatt capacity. Whatever was the load, suppose of 100 megawatt peak capacity, peak rating. So according to that, generator one was already of suppose 100 megawatt rating, as well as transmission line power handling capacity is also of 100 megawatt. But in order to write through these contingencies like generator outage, we should have the reserve capacity of 100 megawatt. This we call it as a reserve capacity because there is no need of this. But under this contingency of generator outage, I need to maintain the continuity of supply. So we should have that much of reserve capacity source. So obviously because of this additional same rated generator we need to install, the cost involved in that is very high. But obviously it will handle the contingency of generator outage. What about the solution for this transmission line outage? Similar to that generator, transmission line also one another parallel transmission line of same capacity. Another transmission line of same capacity I have to build up among these two buses of generator and load, so that if any one of the transmission line fails to another transmission line, I will be able to maintain the continuity of supply. Obviously, under normal condition, both lines may be in regular operation, but obviously their loading will be of their rated 50%. So, in order to improve the reliability of this isolated power system, for each and every component of that power system, we need to have an alternative. Like for source, we need to have the same rated alternative source. That is, we call it as a reserve capacity. We need to build the transmission capacity of double of that load capacity. Obviously, parallel, not a single line will be sufficient of double capacity in order to handle the contingency of transmission line outage. So the cost involved in making this more reliable power system is very high. And ultimately, it is going to affect the per unit cost of an energy. So, here I give you the example of a 5 bus power system. Now, if this every individual power system is every individual bus bar is independent, then obviously in that case, this generator is supposed to feed the load locally here. Means there is no, like said, there is no line. Now, in order to feed the loads at these different locations, what we have to do, we should have the generator at every local area. This local area should have the generator. This local area should have the generator. This local area should have the generator. Again, whatever generator is there in that local area, obviously here it is like that transmission line we consider means what? The generator is, the source is somewhat far away from the load center. Now, as I gave the example of one residential building, in that case, where the load is there, there is a source, like DG said, as I said the example. Or we can consider the example like for an case of an Kharghar city. So let's say Kharghar is a one isolated power system. So whatever source in end is there, like Kharghar substation, rather than connecting that overall whole Kharghar city to that Kharghar substation, let's consider that there is a generator of a capacity of rating of the total load of that Kharghar city. And then from that, please try to understand, there is no mains, 400 kV substation of Kharghar. So let's say the Kharghar city is not connected to that 400 kV substation. It is not connected. There is a one generating station at that substation, and to that it is connected. So there is no interconnection of that Kharghar city with the grid. So in that case, what happens, that generator should be of at least minimum rating of total load of the Kharghar city. In order to improve the reliability, not only single generator is sufficient. Minimum 2 generator has to be there. And obviously the network which is designed there is already might having the 2 underground transmission distribution line cables and that all, because if one fails, the another will be in operation in order to maintain the continuity of supply like this. That is already there. But in order to improve the reliability, separate 2 generators were required there. Like that, suppose there is a one Panvel city, and that Panvel city is also having like a isolated power system, means 2 generators are there and feeding that load. So what happened in both the cases? Every individual power system has a reserve capacity or require a reserve capacity to maintain the same reliability. Means reserve capacity of same rated generator, that whatever total load is there, of that rating generator is there, of that same rating another generator should be there in the reserve in order to maintain the continuity. So here in this example, like that, every city we can call, or district we can call here. Let's say these are 5 districts of Maharashtra. So every district place there is a one generating station, and from that generating station, that whole district distribution network along with somewhat 132 kV level transmission network has been built, and that is equivalently represented here as a one single bus, where that 132 kV bus is connected to the main grid, like that. So every bus is having one generating station along with reserve capacity of the same rated generator. So you can imagine the cost involved in that in order to maintain the reliability. But rather than that, if we simply interconnect that all bus bars through a transmission lines, so obviously this interconnections is decided based on possibilities of every line outage. If suppose for an example this line get out, so under that circumstances this generator can locally manage this, no problem. But whether this generator is of capacity of managing all these 4 buses load, that is also we need to think of. So this system planner were always work out that all things, that if there is any single generator outage is there, or 1 or 2 generator outages there in the power system, still it will not affect the continuity of supply. That has been taken care while designing the system. Similarly, if any one of the lines or 1 or 2 lines get outage, then under that circumstances, again the continuity of supply should not get disturbed. So according to that, that transmission lines were interconnected. So now the question is, the transmission interconnection, why we require to do that actually? So as I said, the cost involved here in this isolated power system is much high. So from the economical point of view, and second is the reliability. Obviously, if we want to more reliable system, then we need to have alternate source of supply, alternate transmission network, and so on. Further, here we are illustrating it only for the transmission level. We are not going in distribution level actually. So if you go to the rural areas, you will find that if there is a fault on 11 kV line, it will totally affect the continuity of supply of all the 4-5 villages which is connected to that 33 by 11 kV substation actually, or which is at somewhat bigger village. So in every district, if you go, there is a villages of somewhat population of 10,000 plus or around 20,000, and to that villages there is a substation that is 33 kV by 11 kV, and through that 11 kV lines, that 3, 4, 5 villages around that somewhat bigger village are radially connected. You know, radial lines are radially connected. So whenever that 11 kV feeder having fault, almost that all villages are in blackout situation. That is what happened. Whereas that 33 kV line come from somewhat taluka place actually, where somewhat 132 by 33 or 66 by 33 kV substation is there, and that 132 kV by 33 substation is at taluka place, where that 132 kV line is coming from somewhat district level, where at that district level there is a substation like our Kharghar substation, where 400 by 132 or 220 stepping down has been done, and that 400 kV was the main, we can say, transmission line of a grid, that is maybe we can say national grid or maybe regional grid. So this is because of that radial design. But here, if you see in the Kharghar city, for an example, it is having some ring main sort of interconnection. Means if one end of the source, one end of the for a particular, we can say, distribution feeder box, if you see, if one end cable fails, till that feeder can be get analyzed to the another end. This continuity of supply has been maintained in that distribution feeder box actually, to which some 4-5 buildings around that distribution feeder has been connected. So whatever transmission interconnections we are doing here, that is in view of making the system economical and reliable. And obviously, in order to make the system economical and reliable, these interconnections are sought at different levels. Like for an example, in Maharashtra, in Mumbai, we can say there is a Tata Power as a one player of electrical power system. Then Reliance is another one, Best is one, along with that MSCDCL is there. So such 4-5 utilities are there. So every individual utility having 3-4 substations. It depends on the we can say size of that utility or how much geographical area that utility is covering. So every individual utility is having 3-4 substations, generating stations, and then 3-4 generating stations are connected to the geographical area to which that utility is feeding the power to a transmission line, such that the continuity of supply to their customer will be get maintained in anyhow condition, if one or two generator fails, still it has to be get maintained, or if any one or two transmission line fails, still it has to be get restored within a minutes and that all. So like that way, the transmission lines are interconnected there to the generating stations and the load section. So that we call it as a internal utility interconnection. Means within that region of utility, there is an interconnection of its own actually, of its generating stations and the load through a transmission. Like that, every utility has the interconnection in their own geographical area. Still, that different utilities, again, in order to improve the more reliability, if that utility or generating station fails or something wrong happens with them, till they should be able to maintain the continuity of supply, or maybe in view of taking the and other advantages, like for an example, you might be knowing that developing the generating station in nearby Bombay region may be a very costly affair. So earlier it might be get developed, but now it is very difficult. So that particular utility may procure a land somewhere far away from Bombay, and they will have their power plant there. And through this national grid or maybe regional grid, they will bring that power to their area. So obviously it has to be get integrated with the infrastructure which is there available in that geographical area where they install their own power plant and that all. So in short, what I want to say that every utility having interconnection in their region, and then that there is an interconnection between the inter-utility. This utilities having the interconnection with each other. So that is, we can call it as the inter-utility interconnection. This in Maharashtra we can say that there is a inter-utility interconnections among MSCDCL, Tata Power, Base, Reliance, and that on. And obviously the network to which these all utilities are connected, then we can call it as a one state level grid. Obviously it is not a simple state level grid, it is basically a regional grid. It is not state dependent basically. That is region dependent, like Western region, if we talk about then Gujarat, MP, Maharashtra, Chhattisgarh. So like that, states are there having a one separate grid to which the all utilities in that states are connected. And through that grid, they have the exchange of power. Means the exchange of power amongst the utility can be done through that grid. Similarly, like Western region, there is a northern region, western region, southern, northern region, southern region, central region, and eastern region. So these all regions again having their interconnection with each other, and that is called as the national grid. Means over one nation there is a one grid, that is we call it as a national grid, and to which all regions are connected. Where in that region, 3-4 states are interconnected. In every state, there is a number of players which are interconnected. So like that way the interconnections were done in order to make the power system more economical and reliable. So hope you understand what I want to say here, why we need to do the interconnection. So as I said, the interconnection is done in view of making the system more economical and reliable. Making the system more economical and reliable actually. Along with that, how it can be made more economical, there is a lot of explanation for that. Like some power plants are hydropower plants, some power plants are thermal power plants, some are nuclear, some are renewable energy source based. And obviously, getting a power out of that different power plants will be at different rates because the cost involved in them regarding their operational cost, if we talk, are varying. For hydropower plant, the operational cost is very poor, less. Whereas for thermal power plant, it is very high because the raw material involved in that is the coal. So coal cost, transportation, that all things are there. Whereas for hydro, only to construct the water dam once it is constructed. So there is no any cost has to pay for purchasing the water or transferring that water and so on. So because of that, the operational cost of it is very less. So interconnecting such a different form of sources to these interconnections will make the system economically operational. How, let's say for an example, if there is a rainy season, so all dams are full of water. So in that period, obviously, we will use the hydropower plants as a base load power plants. You might be heard the word base load power plant and peak load power plant. Base load means those who are working continuously for 24 hours. Is given as priority as per economical generation scheduling which we studied in last semester. So hydropower plants are given the priority to operate continuously, and whenever the demand is greater than this peak demand is there, so during that period only thermal power can be utilized. But obviously, we all know that the starting time and stopping time of thermal power plant is in hour section, whereas that of hydropower plant is in minutes it can be started. So, but if you look the daily load curve, from that it is very well known the nature of load. So during what time the peak will be there. So before that an hour or as per the requirement of the thermal power plant starting stopping time, we can utilize that. So in that case, what happens during that period, the cost for generating the power gets minimized. But obviously in the summer season, the availability of water in the dam is less, so that is reserved for drinking purpose and that all, or agriculture purpose somewhat. So cannot be get utilized for generating the electrical power. So under that circumstances, it can be used only peak load power plant. Base load power plants are like our renewable thermal and nuclear and so on. So here the diversity of generation can be utilized in order to minimize the cost. Similar to that, the diversity of load is also can be done. Like as we know, during the 24 hours of load cycle, there are peak load periods, your normal load periods, and that all. So in order to motivate the customers to consume the power during normal load period, means base load period, rather than consuming it during the peak load hour section. So for that, they motivate by giving some tariff system based on that actually. Means you might be heard that there are 4 cycles in a day for the tariff. In the first morning cycle, the charges are high, and in the evening third cycle, the charges are also high, whereas in the afternoon cycle and in the night hours, the charges are less. During night hours, the charges are much less actually. So why it is done? Those who are able to stagger their load according to that cycle. Let's say for an example, nowadays you might be hearing that the agricultural loads, they are getting in light of only 8 hours a day, and in a week 3 days they are getting in daytime, and in remaining 3 to 4 days they are getting in the night hour. But if we observe that timing, so you will come to know that how it is getting managed. So timing is always, if they are giving in daytime, if they are giving the light in daytime, the timing is around 8 a.m. to evening 4 p.m. or 9 a.m. to evening 5 p.m. Means they avoid that very peak load hours. Like early morning, there is a very peak, and early evening, there is also, or evening we can call it, there is a peak there. And in night hours, they are giving by the time of night 10 o'clock to morning uh, 6 o'clock, or maybe 9 o'clock to 5 o'clock. Why they are doing so? Because they are knowing that farmers for agricultural loads, they are not paying for that on time. So they are not getting as much revenue out of it. But still, as a, we can say, part of government, because it's a government undertaking companies like energy and that. They has to serve them also. So they are managing in that according to they develop the strategies such that uh, they can manage their overall system by delivering the load to them also, rather than curtailing. So these all things are possible because of an interconnection of the transmission. So hope you are understanding. In order to make economical and reliable power system, the interconnections is important. But at the another end, this interconnection makes the network very complex actually. This interconnection makes the network very complex. So it is very difficult to operate such a network, and because of that, it becomes less secured actually. Less secured means if there is a fault on any one of the line, so till the period of getting it disconnected, the whole system get affected. Obviously, it is depends on the size of that transient, see how large was that transient and how long that transient exists on the system. Obviously, how long that transient exists on the system is depends on the protective system, that is relay sensing devices, fault sensing devices, operation of relay, and operation of circuit breakers. So these all will going to decide total fault clearing time and that all. But if that fault is of very large size and prolonged for a longer period, then during that period the power oscillations will be get created, and that power oscillations, if not get damped out, then the whole system may collapse. So this is requiring a very fast operating protective system. This is requiring a very fast acting protective system. Similarly, the another problem is like when many more transmission lines are interconnected to each other. So under that circumstances, what happens? When we plan out the generation at different generating stations according to generation schedule, and for that generation, if you do the load flow study, you will find that some lines in that network may get overload if we operate the system according to that economical generation schedule. And some lines may be very underloaded. So such situations may be arise. Obviously, during the initial planning time, it wasn't so, but after some years, that situation may arise. So under that circumstances, to handle this, we need to go with the upgradation of the network. Means those network getting overloaded. So we need to upgrade that network. Means modify their power handling capacity and so on. So very large cost involved in that actually. But rather than that, if by means of some power electronic device, we can regulate the parameter of that transmission line such that we will limit the power flow through it and pass it through the underloaded line. Obviously, that is possible if we have a flexibly flexible flexible AC transmission system. Flexible AC transmission system is if we have some fast controller connected to that line, which will increase the impedance of that line so that power flow through will be get limited and it will be get automatically diverted to the other parallel path available in the network. So that is what we can say, looking the opportunity for threat devices in such cases. So that is, we call it as a bottleneck, means the network is there and one particular line is acting like a bottleneck, means it's already uh, power handling capacity is such a load, means is such that uh, under different generating scheduling cases, the load flows in that circumstances, that line is getting overloaded as well, and we can't operate it. So obviously, we need to plan out or develop some another parallel transmission line along with it, or modify the parameters of other lines or that line itself such that that bottleneck can be removed. So this is the one problem. As I said, less secured it becomes. So in order to handle it, very fast acting protective system will be required here. And at the same time, some bottleneck may be exist, and to overcome them, there is opportunity for flight devices. Another case is, as we saw all around circuit breakers, isolators, and that all. So these all are mechanically controlled devices. So these are mechanical devices, we can say. Similarly, there is a widespread use of computers, microelectronics, and high-speed communication system for the protection of a power system or for the operation of the power system. Now, as we all know that, let's consider from the protection point of view. When relay sense means relay is not going to sense whether there is a normality or abnormality. So some CT is there. Let's say for an example, CT current transformer is there on the line, whose output is given to your communication cables or signals. That signals are given to your processing devices like computers, where it has been monitored regularly. It is not manually monitored. It is monitored by the software based or computer based, we can say. And according to that values, it is get judged whether there is a normality or abnormality and so on. So there is a communication of that signal from CT to computer comes. So that should be again high speed, because what is the time constant of CT? What is the speed of transfer of that signal to the computer? What is the speed of processing of your computer? According to that, whatever output signal of that computer is there, that is, it will forward to your uh, as a controlling signal to the circuit breaker. Then again, the speed of that signal, time constant of circuit breaker, that is operational time constant of circuit breaker after getting that signal, how much time it will take to open or close. So the time of this all is involved, and that is all affect the operation of the power system. अगर कोई भी abnormality आया, उसके बाद वो abnormality पूरा प्रोसेस होके उसके अगेंस्ट जो प्रोटेक्शन ओपनिंग वगैरह जो भी करना है सर्किट ब्रेकर का, वो कितना फास्ट होता है, that all is going to decide whether the system will be stable after clearing of that fault or not. That is what we already studied in power system. That is critical clearing time, critical clearing angle, and so on. So this again, these mechanically switch devices are having a very large time constant. Let's say for an example, if we have a mechanical switch, as we say in our house, there is a one mechanical switch to turn on your electrical appliances and turn off them. So the on and off that time period by doing it manually. Rather than that, if we have some power semiconductor devices as a switch, so their speed of operation is very fast. Power semiconductor devices. Again, the number of operations are very large. You all might be knowing that if we talk about switch, so the life of that switch, if we talk, it is not counted in terms of years. If I year switch ka life 10 साल है, 20 साल है, 30 साल है, it is not counted in terms of that. It is counted in terms of number of operations. Like this switch is having an 5,000 operations. Like this switch is having a life of 10,000 operations. Means 10,000 turn and off it can sustain. But if we go with the power semiconductor switches like our diode, track, drag, UVA, so their number of operations are hundreds of times of that your mechanical switches. So there is again one opportunity for the power semiconductor devices to be used in a power system for effective improvement in the operation, and operation may be steady state or transient based of the power system. So this is what about the interconnection of transmission system, what problems will come with that. So in general or in summary, you please keep in your mind that we are doing the interconnection of the transmission lines for economical and reliable purpose. But along with that, it comes with the less security, complex network, so increases the problem of protecting such a systems and that all. So that is requiring high speed controls and that all. But again, for that, if there is a mechanical based control, then their time of operation is very high. So for that, replacing that mechanical control by some part on controls, so that sort of opportunity is there again. So this is what about the transmission line interconnection. About opportunities, I was already mentioned to you that first opportunity was in general, that is as the performance of the transmission line is governed by its parameters, that is resistance, inductance, capacitance, and conductance. Out of that, resistance and inductance are series connected, whereas capacitance and conductance are parallel connected elements. So these elements, these elements are governing the operation of a transmission line. अभी ये जो एलिमेंट बोल रहा हूँ रेजिस्टेंस इंडक्टेंस कैपेसिटेंस कंडक्टेंस that are going to decide for the given sending end voltage what will be the receiving end voltage, what will be the voltage drop across it, how much will be the current flowing through the line, how much real power is flowing through the line, how much reactive power is flowing through the line, what will be the angle of receiving end voltage for the given sending end voltage angle and magnitude. So these all depends on this parameter. And obviously, these all is nothing but the performance of a transmission line. Like carrying a more current means it will carry the more power. Maintaining the voltage within the acceptable limit. Power loss should be minimum so that it should be efficient. Means, but as I said in the discussion of transmission interconnection, many transmission lines may get overloaded. Means for a given generation scheduling, please try to understand, given generation scheduling means in a given power system, there are generators at different locations, loads are at different locations. According to forecasted load, the generation schedule, economical generation scheduling has done. मतलब कौन सा जनरेटर ने कितना पावर जनरेट करना है वो टाइम, वो जनरेशन शेड्यूल करने के बाद we will do the load flow study to check वो जनरेशन होगा तो वो केसेस में कौन से लाइन में से कितना पावर फ्लो होगा, is any line getting overloaded, is any bus voltage is going to be cross the acceptable limits, so that all things are first analytically verified, and once it is satisfied, then and then the system is actually operated with that considered power generations and that all. So if after planning, while planning it has been taken care of all factors, but after decades, what happened? The loads are increasing and that all. And obviously, it is not linearly varying at all the regions. Some regions it is largely increasing. Some regions it is very slow. Let's say, for an example, if you took the example of Mumbai, so the transmission networks which were designed some 50 years ago, at that time, whatever progressive increase in the load of Mumbai was considered, obviously that time, whatever was the situation, it might be very slow compared with nowadays it was increasing. So these all factors changes in the consideration has changed the actual requirement of the system. So under that circumstances, the line which we expect to be uh, served for some 30 years, 40 years without getting overloaded, but may achieve the overload rating as before. So under that circumstances, we need to upgrade that transmission line. But along with that, another lines may be there which are underloaded. So through that line, it may be transferred. Please try to understand that. Let's consider the example of Kharghar substation. Now, Kharghar substation, if we see 400 kV, there is not a single transmission line connected to that substation. There are many more transmission lines. I think 3-4 transmission lines are connected to that 400 kV substation. What it means? Means this busbar is having 3-4 transmission lines where that 4 transmission lines are coming from different locations. Coming from different locations. So let's say one is maybe coming from Konkan, one is maybe coming through somewhat center of Maharashtra, one may be coming through uh, western part of Maharashtra. So like that, that lines are connected to that Kharghar substation. So whatever power we are taking at Kharghar substation, along with that, some power from this line to another line, like that way it is flowing. So under such circumstances, if any one line connected to that Kharghar substation is now already achieved its flow through to its rated capacity. So under that circumstances, what happens? We need to modify that line. Else, for every loading condition, that line will be get overloaded. So either we need to upgrade that line or go with some alternate based or static devices to modify the parameters of that line such that the power which is anonymously coming through it will be get diverted to the another transmission line. So that is possible if the patch controlled devices are there. So that is what we are going to study in detail in the coming lecture section. So that is the first opportunity for the patch devices. Second is, as I said, some mechanical replaced by that power controllers and that all. So whatever I discussed here about the rise in the speed of response and that all. So that is, there is the opportunities for patch controller. Here one example is given of I think that energy SSR damping scheme. Okay. How much is the time? Oh, it's already 2:30. So we can stop here. In tomorrow's lecture, we will see flow of power in the AC system, how the power flows in the AC transmission system, which is not controllable, and how with the patch controller we can control that power flow. So this understanding we will get from the coming lecture. You all please mark your attendance. I'm just activating the link for submission of your attendance. Please mark your attendance. Those who mark the attendance can leave the bit, no problem.